monomer reactivity ratio and mole fraction of the feed and mole fraction in the copolymer system, which was represented as a small F1 and large F1. Okay? And now I think we need to know about how we can experimentally determine monomer reactivity ratio R1 and R2. Okay? You remember that the copolymer equation can be expressed as a dm1 over dm2 is equal to m1 over m2, and m1, m2, and r1 and r2 could be applied in the equations. But if you could rearrange your copolymer equation in terms of r1 and r2, whereas r2 here in this case could be such as a y, and r1 could be the x. Okay? Assuming that you know M1 and M2, because M1 and M2 is the monomer reactivity ratio, monomer mole fraction, monomer concentration in the feed, okay? Whereas DM1 and DM2 could be the monomer concentration in the copolymer systems, okay? So if you can determine the mole fraction or mole concentration in the copolymer, okay, such as by using NMR and other techniques, okay, then you will know M1 and M2 and DM1 and DM2, which is regarded as a constant here in this case. So if you change, well, so what you can do is that you can change the concentration of your M1 and concentration of monomer 2, so that you will have a copolymer system, with a given concentration of M1 and M2. Okay? And then you can determine your DM1 and DM2 in your copolymer system. So this is one point. Okay? And then you can repeat and change M1 and M2 and get the DM1 and DM2, stuff like that. So if you have at least 3 or 5 points of each case, by changing your monomer composition and determine your copolymer composition, what you can do is that you will calculate these values, which is constant, and these values, except R1 and R2. So what you can do is that you will plot Y, which is R2, and X, R1, and by changing the composition, then you will see the slope, okay, and intercept, okay, at each composition. And here in this case, we have at least 3 experiments. So if you conduct 3 experiments at least, what you can do is that you can see, this is first experiment, second experiment, third experiment, then you will see the triangle, okay, between these 3 points, which is regarded as R1 and R2 in this case. Okay, so this way, the perfect value might be, there is no triangle, but if you have a smaller triangle, then that's the point where you can determine your R1 and R2. Okay. This is one way of measuring and calculating the R1 and R2 by experimental measurement of copolymer composition, okay, at a given monomer composition. Okay. This is what they call the Mayo and Lewis method. Okay. Mayo and Lewis devised this way of measuring the R1 and R2 by varying the monomer composition and determining the copolymer composition in your copolymer systems. So smaller the triangle, then you will have a better R1 and more precise value that you can get in R1 and R2. Second method is called the Feynman and Ross method, whereas they did almost the same thing. Okay, you will see the large F1. You remember that the Copolymer equation, large F1 is equal to, or as a function of small f1 and f2 and r1 and r2. Okay? So if you rearrange this equation in such a way that you have a constant is equal to r2 plus constant times r1. Okay? In this case, A is equal to R2 plus B R1, and with the same analogy, if you change small f1, okay, if you change the small f1, feed mole fraction, okay, and then you can get the copolymer mole fraction of 1, component 1, okay, then I think you can get the different constant values at a given f1. So if you plot at least 3 or 4 points, then you get a linear plot, because you have if you vary the b, then you get a different a values, which must be constant, so that the slope will be r1 and the intercept will be r2. Okay? So if you can get the slope then of these plots, at least 3 or 5 points of the b constant and a constant, because by changing the small f1, you get a different and get a large f1, then you have a different b constants, b1, b2, b3. At a given b1, b2, b3, you get a1, a2, and a3 values, so that you should have a linear plot, because it's theoretically it's a constant. A and b should be constant. Okay, so from the slope of slope you can get the r1, and from the intercept you can get the r2. So this way, experimentally, you can determine R1 and R2, monoreactivity ratio of the two copolymer systems. But you do not need to experiment to determine these cases. This is, textbook, the method of measuring the R1 and R2. This R1 and R2 has already been determined in many, polymeric systems. So you do not need to measure, but what I have emphasized was, well, this is the way of measuring R1 and R2. But in the textbook, even in the table, the R1 and R2 has already been given. So we will see later on what about the R1 and R2 values. I think I will skip this, the eta, okay. And what about the reaction conditions? Reaction conditions such as solubility, pH, viscosity, and polarity will affect the monomer reactivity and other conditions. What about the temperature? Does temperature affect the monomer reactivity constant? Well, the monomer reactivity ratio is defined as a ratio of the different kinetic constants, and as you have already been known, the kinetic constants of each case should be related with the Arrhenius equation, and from this Arrhenius equation, you can easily say that, well, reactivity ratio, monomer reactivity ratio, should be dependent upon the temperature. So temperature should affect the monomer reactivity ratio, but in fact, there is not much difference between these two, the activation energy for the radical and the monomer cases. So the dependence is not great. not that great as we have expected. Pressure should have affected the monomer reactivity ratio from this equation, but the dependence is not that much as in the case of temperature. The reactivity is, of course, will affect the monomer reactivity ratio. Well, before we go in more detail about the monomer reactivity ratio, we should know about the radical reactivity ratio as well. That's why I have given you a homework that please derive some equation about the radical reactivity ratio, because you know the monomer reactivity ratio definitions. Well, we will talk about the reactivity, but reactivity depended much upon the structure of your monomer. Structure of your monomer will greatly influence the reactivity of your monomer systems. And I think I will explain this structure and reactivity relationship in 3 points. First one is about the resonance stabilization. Secondly, the polar effects. Finally, we'll talk about the steric effect. The first discussion point will be the resonance stabilization. Okay? Now, you all know what is the resonance stabilizations. Okay? But let me start this discussion from this table. Okay? If you take a look at this table, we have a vinyl group and substituents, all. Okay? All could be hydrogen. If it's hydrogen, we call this as ethylene, right? If you have a methoxy group, then this is called methyl vinyl ether. If you have a Cl, we call this as a vinyl chloride. If you have a benzene, we call this is styrene, right? So you change your all into double bonds with the different substituent groups, and the relative reactivity of your monomer, assuming that the reactivity of the monomer in ethylene is 1, relative reactivity will perhaps increase with the type of your substituent groups. So there might be something happening, and looks like that the structure of your monomer will greatly influence your reactivity, right? And the stabilization energy will, of course, increase in this case. I have 2 columns. This is just substituent groups, and this is the radical, meaning that if your monomer will become radical, then you have a stabilization energy as well. So from this point, from this table, we can see that structure of your substituent group, in other words, structure of your monomer, greatly influence the reactivity of your monomeric systems. Okay? Now, this is the one monomer systems, but we are talking about the copolymer systems. Okay? So we have to know the 2 monomeric systems. Before we go further, this is why I think I have to, I have asked you to do the homework by Friday, by today. Otherwise, you have your solution here. Now, monomer reactivity ratios has been defined as K11 over K12, or KAA or KAB, where the monomer reactivity of A. Monomer reactivity of B, or Al2, is equal to K22 divided by K21, or KBB divided by KBA. Okay? What about the active center reactivity ratio, okay, or radical reactivity ratio? Large array large LB is K11 divided by, not K12, but K21. Okay? So denominator is just exchanged in this case. Okay? Nominator is about the same, but denominator is just exchanged with the small array and the large array. Therefore, if you know the large array could be KAA divided by KBA, right? But if you just multiply both numerator and denominator, then KBB, then you can come up with small lb times KAA over KBB, right? So there might be something correlation between small r and large r. Okay? Small r and large r, in other words, monomer reactivity ratio should have some relationship with active center reactivity ratio. That's why I've emphasized that you need to define the active center reactivity ratios. So, large array is equal to small lb times Ka over Kbb, whereas larger b is equal to small array times Kbb over Kaa. Okay? So monomer reactivity ratio, again, has some relationship with the radical reactivity ratio or active center reactivity ratio, but A and B might be different, okay, here in this case. Okay, we have a very complicated table here. Let me start. We have RA and RB, small RA and small RB, which was defined already, okay, in previous slides, where small RA and small RB is monomer reactivity ratios of monomer A and B. Large RA and large LB is active center reactivity ratio or radical reactivity ratio of A and B. Okay. Now we have another two columns, monomer A and monomer B. Monomer A could be AN. AN is what? Acrylonitrile. Okay. And for the same monomer, you have a different the second monomers. This is methacrylate, methyl methacrylate, styrene, vinyl acetate, and so on. So you see all those codes, right? Now, you fix the first monomer, but you change the second monomer. The KAA for AN monomer system is about the same, but KBB is different here in this case. But you can see the small RA and small LB. Small RA for the same monomer, but the different second monomer will change. Small RA changes, of course, the small LB changes. Large RA changes, large LB changes. Although we fixed the first monomer. If you change the second monomer, then everything changes. What happened? In other words, monomer reactivity ratio is not the fixed value and should be changed by changing your monomer systems, A and B. So if you change B, then everything changes. But there are some trends. You see, if you can take a look at these 4 lines for AN monomers, RA. If you have a large RA, if you have a larger, small RA and smaller LB, small LB, large array is always smaller than large LB. In other words, small array here in this case is 1.26. Small LB is 0.67. Large array and large LB, if you compare these two values, large LB is much larger than large array. Whereas small array is larger than small LB. If you take a look at the second row, 0.1, 1.2, 4.7, 3.94 times 10 to the minus 2. So, if you have a larger small array, your large array is always smaller than large LB, right? Right? So there are some trends, you know? And that's the same thing for everything. You know, if you change your monomer systems from AN to MA or MMA, and change your second monomer, then everything is about the same. Small array and large array. If you have a larger small array, if your large array is always smaller than large LB. So we can say that if your small LB value is larger than small array, then larger B is always smaller than large array. Okay? This is what I have stated, and I have concluded from this table. Now, what happened? Okay. And this was defined as copolymerization of your the active center reactivity ratio. Okay. So the relative reactivity of active center has much more stronger influence than the monomer reactivity ratio. Okay. Large array ratio is always greater than small array ratio. This is what we have also concluded in this case. So the factor that influences to your monomer reactivity ratio, okay, will much more greatly influence your active center reactivity ratio, which is large R. And monomer reactivity affects the opposite way compared to the active center reactivity, which I have just elaborated here in this case. So there are something happen, right? If you have some factor influencing your monomer reactivity ratio, that influence the radical reactivity ratio or active center reactivity ratio in opposite way, but the factor will much more greatly influence the active center reactivity ratio than the monomer reactivity ratios. Okay, this is what we can conclude from the active center reactivity ratio definitions. We can take a look at the second table. Well, we have a butadiene, styrene, methyl methacrylate, stuff like that, and vinyl chloride and vinyl acetate. But radical, this is the monomer. Butadiene monomer will meet the butadiene radical. Butadiene monomer will meet the styrene radical, stuff like that. So you can see the relative reactivity of the monomers versus the radical, which was given in this right-hand side. If you take a look at these values, there might be some trends. The value will increase from the bottom to the top. bottom to top, bottom to top, bottom to top, but there might be some inconsistency, but relatively it could be true, right? This is not consistent. Although there are some points where we cannot generalize this conclusion, but you see the arrow of the increasing the number is coming from bottom to the top, or left to right. In some cases, there are some the discrepancies, of course. So what you can see is that the monomer from bottom to top is about the monomer at a given radicals. At a given radical, monomer relative reactivity of the monomer increases from bottom to top. Okay, bottom to top means that you have a vinyl and another vinyl for butadiene. Or you have a conjugated structure. So if you have a conjugated structure in your vinyl group containing monomeric systems, your reactivity increases. Your monomer reactivity increases from bottom to top. But from right to left, in other words, if the radical has a conjugated structure or a resonance stabilization, then the reactivity goes down. Reactivity increases inversely from left to right rather than right to left. Right? Okay. So this is what I can say. Okay? Your monomer reactivity increases when you have your conjugated structure. When you have a resonance stabilization, your monomer reactivity increases. But those radical which has the stabilized structure is not reactive anymore. Okay. So this is what your arrow indicates. Your arrow is coming from bottom to top, indicating that you have a conjugated structure in your monomer, whereas radical reactivity is always greater at the right-hand side. The radicals at the right-hand side, those radical does not contain the conjugated structure. So this is the conclusion from this table, and therefore substituent effect of the substituent groups is that your monomer reactivity always increases when you have your resonance stabilized substituent groups, right? However, resonance stabilized the substituent group, when it becomes radical, is not reactive anymore. So the reactivity of those radicals having the resonance stabilized structure is quite weakened. Therefore, the reactivity is quite decreased in this case. So monomer reactivity ratio is from right to left, whereas if it becomes radical, reactivity of the radical is from left to right. Okay? Now I have another table okay, saying that the rate constants, instead of our relative reactivity, we can take a look at the rate constants, K11 or K12 or K22, stuff like that. And you see, if I have a monomer butadiene styrene, which is the same order as before, but the radical, if it becomes a radical, then you can clearly see the number increases from bottom to top, the bottom to top, yes, bottom to top at a given column, right? For a given acrylonitrile radical, your reactivity of your butadiene and acrylonitrile radical is about 98,000 in the rate constants, whereas acrylonitrile monomer and acrylonitrile radical is about 2,000, right? So there is a clear evidence that the relative rate constant K12 increases from bottom to top, having your substituting group with a resonance stabilized monomer, your monomer reactivity increases. Whereas if this number increases from left to right rather than right to left. In other words, if those radical having the resonance stabilized structure, in this case the butadiene, the styrene radical, has always the lower in number of those K12 than those monomer radical, which does not have any resonance stabilization, right? So the conclusion about the structure of your monomer and the structure of your radical is quite opposite, okay? If you go back to your equation, small RA and large RA or large LB is defined as a function of a small RA, right? Large LB is defined as a function of a small lb. So I said it's opposite. A and B, large RA and small lb is quite opposite in this case. Could be evidenced and could be applied here in this case. In the last two columns, I have two values, Q1 and E1. Q1 is resonance stabilization effect. Okay, Q1 is a resonance stabilization effect. So if Q1 increases from bottom to top, so arrow is indicating that this increases, whereas E1 is a polar effect. E1 is a polar effect, and polar effect is not the same as Q1 trends. Okay? So I will tell you what about E1. Okay? But Q1 indicates that if you have the resonance stabilization, then Q1 value increases. Remember that Q1 is 1 for styrene. 1 for styrene. The styrene was standard material for QE scheme, whereas E, polar effect, for the styrene, it was arbitrarily set to minus 0.8, and I will show you why they set minus 0.8. Well, I don't know actually, but they arbitrarily set this styrene is a standard material for their calculation for Q and E. And instead of minus 1 or 1 for styrene, for E, maybe they have quite phenomenologically determined this E value for minus 0.8. Okay, so resonance stabilization could be one of the reasons for the affecting the monomer reactivity ratio and the radical reactivity ratios. So we will come back to the monomer reactivity and the radical reactivity. Okay? The conclusion will be given in this table in your next slide, next 2 slides after. This is quite complicated, so I will go back to the basics of the Lennard-Jones potential. So we need to know the resonance stabilization. So, for example, if I have a ester and I have a radical, this radical or the electron will be moving to next carbon, and the carbonyl carbon may add the electrons to form the double bonds here, and your electron will be moving to, in other words, moving to oxygen rather than this, the presence of the carbons. So the electron will be something like moving to, in this plane. This is what we call the resonance stabilization of your radicals. Okay. Now, if you take a look at the Lennard-Jones potential energy diagram, potential energy will be decreasing, will be constant, of course, but increase as your 2 atoms get together. Okay, A and B atoms get together. Then you have to overcome your activation energy between your states, assuming that you have an activated complex, which is mountain, and the distance from the top of your mountain to the level where you start is called the activation energy, right? And you have to overcome your activation energy, and it comes down to the very stabilizer state, where we have the minimum potential energy. Okay? The distance between the minimum potential energy with the existing state is called the enthalpy changes of your reaction, delta HL. Okay? And then if you have a further closer between the A and B atoms, then you have a repulsion. Okay? So attraction and repulsion, okay, here in this case. If you divide the potential energy between the A and B, then I have A and B, attractive forces will follow this line, whereas your repulsion will increase from the minimum potential energy. Okay? So this is the attraction line, whereas this is the repulsion line. Okay? If you can divide this curve into activation at the attraction and repulsion, then we can break down into these 2 places. So I think I have modified this, but it was not given here. If I have a given radical, R, I have R. I have M, okay, and MS. S means stabilized monomer, such as styrene and butadiene, whereas M could be non-stabilized monomer. So if I can describe this, differentiate between the MS stabilized monomer, which has a much higher reactivity than M, which does not have any stabilization, then it becomes R, of course, if it becomes a radical. MS will become RS, right? So I have 4 species. Therefore, I can have I have a large R, which is radical, and I have RS. RS is the monomer RS. MS becomes RS, right? RS, attractive forces. And I have a repulsion forces because of the reaction between R and M, and R and MS, RS and M, and RS and MS. So I have 4 different cases. This is too complicated, so let me explain with this simplified version. I have R, but I have a M and MS. Excuse me, I think this is the MS. Yeah, R and MS. If I have a R and M reaction, the activation energy is from this point to this point. So it's about delta E1. If I have a reaction for the repulsion, in this case, this and this level, not this one, but this level is a delta E3. Okay, and the red line is correct. From here to here is delta HL1. Here to here is a delta HL3. So please correct. I think I have to move this arrow up to here. This delta E3. This delta E1. Anyway, you can determine the magnitude of delta E and delta HR between the 4 reactions. So that's the next slide, where we can determine, delta E and delta H, delta E and delta H, stuff like that. So there are 4 delta E's and there are 4 delta H's, okay, in different arrows. So what about the values? What about the delta E? This is too complicated. This is too busy table. So let me summarize those values. And that was given in here in this table, where if you have R and MS, which becomes RS, R and M becomes R, RS meeting with the MS will become RS, RS meet with M will become R. And I have a delta H. They measure the delta H value. They measure the delta E values and tabulized here in this table. Delta E increases from top to the bottom. Delta H value will also increase from top to the bottom. Oh, excuse me, from bottom to top. Okay. So if you have a larger delta E value, then means that you have to overcome those high magnitude of your mountain. Okay? So it's difficult to overcome when you have a larger delta E values, activation energies. So the reaction is much easier in the first case and difficult in the fourth case. Now, if you take a look at the first and second row, R is the same, and the difference is MS and M. So when you have MS, in other words, a stabilized monomer, just like a butadiene and styrene, you have larger reactivity. Therefore, it's much easier to go ahead with your copolymerization, and that was evidenced by the lower activation energy. Whereas you have a larger heat of the enthalpy, and this is the negative. Therefore, it will contribute to your it will contribute to your negative, the Gibbs free energy of difference, right? If you remember delta G is defined as delta H minus T delta S, and delta G should be negative for your polymerization reaction, okay, to become the spontaneously occurred. Therefore, if you have a larger minus delta H, that means it's much easier to proceed with the copolymerizations. So, first column is the most probable reaction with the high reactivity and high probability and low activation energy. If you remember these two cases, R, MS, RM, so MS is much better than M, right, in terms of the reactivity. And that is also the same for RS and MS cases. If you remember third and fourth columns, MS is always much easier than M, whereas R is easier than or much more reactive than RS, right? So MS is pretty good for your reactivity, and R is reactive rather than RS. So this concludes that our discussion about the structure and reactivity in terms of the resonance stabilization. Okay? So if you ever stabilize the monomer, reactivity is very high, evidenced by MS. But those monomer which becomes RS is much less reactive than R. And there was also, summarized in our active center reactivity ratio versus the monoreactivity ratio, small r and large r. So, any question about this resonance stabilization? Okay, I think we can go ahead with the polar effect and the static effect. And if you have some time, I think I will give you a summary in Korean. Now, next topic is about the polar effect. Polar effect is the one that does, styrene again was a standard in the QE scheme. And there are some values beside this monomer. The styrene is minus 0.8, vinyl acetate minus 0.88, stuff like that. So you see the number after your monomer name, okay? Name of the monomer. So this in your copolymerization systems, you see, when you have a much smaller RA and RB, then I said we have a tendency to form the alternating copolymers. If R1 and R2 is close to zero or zero, then we have alternating copolymers. Okay, when R1 and R2 or RA and RB is much less than 1, then we have alternating copolymers. So E value here represents the monomer polar effect of your monomer. The Alfray and Price, the two well-known polymer physicists and chemists, defined the polarity values. And what they've done was that they defined the RA and RB in terms of the rate constants, the K11 or K12 or whatever. So I and J represents the two species. Okay? and they define this Kij as a Pi, which is the active center reactivity ratio, active center reactivity, and the Q as a monomer reactivity to the exponential minus EI and EJ, and E in this case is a polar effect. Okay? For example, the polar effect constant for styrene is minus 0.8. Okay? So if you know E1 and EI and EJ between the two spaces I and J, and knowing the P and Q, then you can calculate the Kij. That's what his definition. So, for example, Ri is defined as Kii divided by Kij, and Kij is here, and Kii will be, you replace this J with I, and given in this equation. And here you can cancel the same, the Pi here up and down, and Qi and Qj left, and if you can rearrange, exponential minus EI and EI minus EJ. Therefore, what you can see is that if you know the monomer reactivity Q value and E value, then you can calculate the R value. That's what the Alpha and Price suggested to the QE scheme. So QE scheme is quite well known at the time, because you do not need to complicate the experimental determination of R1 and R2, just like what I have introduced to you at the beginning with the Feynman and Ross and Mayer and Lewis method. So this equation forecasts the R because you know Q and E values. But this value, Q value and E value, was quite arbitrarily set. There is no theoretical background about this arbitrarily setting the styrene as a standard and 1 and minus 0.8. There is no ground, but they just set up the standard, the styrene, and other cases. So this is a pretty fair results in predicting the R value using this Q scheme. Now you know that the Ri, but let's talk about Rj. Rj will be simplified with a Qj and Qi with exponential E or something. Okay, if you multiply Ri and Rj, then you can cancel out these Q values and come up with exponential minus EI and EJ to the square. Now, if you look at this value, EI and EJ to the square, whatever value is, if it's positive, between the bracket, then square will be, of course, positive. If it's negative, if you multiply this, the square, and then to the minus will be something that is given, and you see those value between the exponential is always less than 1. Therefore, RR and RJ is always less than 1, and this indicates you're predicting the alternating tendency from this QE scheme. So the alternating tendency is correct from this QE scheme as well. You can predict the PE scheme instead of QE scheme, but it's a little advanced in the polymer chemistry. But anyway, you have a QE scheme here, but you have a P and E scheme as given in here in this case as well, by defining the large Ri and large Lj in this case. Okay? But this is a little advanced polymer chemistry, so I will not go more in detail in this case. So we have talked about the QE scheme, but there are some criticism about this QE scheme because styrene was set at arbitrarily, and alternating tendency was observed because of the polar effect. That's what the Alpha and Price argued. But in fact, there are some charge effects and not due to the induced dipole moments. So there are some criticism about this alpha per QE scheme. But anyway, this is one way of introducing the QE scheme in the polymer chemistry recently. Let's talk about the another polar effect and static effect. Now, we talked about the polar effect, but let's talk about the static effect, in fact. Now, this monomer is what? This is, if X is equal to Cl, we call this as a polyvinylidene fluoride, vinylidene chloride. Or if X is F, fluorine, we call this as a polyvinylidene fluoride, PVDF, or PVDC. PVDC is much more stable than PVC. Okay, PVC is made with just one X instead of 2X. If you have 2X in one carbon, we call this as a polyvinylidene chloride. Polyvinylidene chloride. So PVC is quite widely, used in Korea for our, the floor coverings and wallpapers, and even the films, wraps. But PVDC has been used in the wrapping industry as a saran wrap from Dow Chemical because of the much higher stability of PVDC than PVC. PVC is less stable than PVDC. Therefore, PVDC is much more popular. And if you replace the Cl with fluorine, this is called PVDF. Okay. Now, PVDF is much more reactive than PVC. In other words, this is the 1,1 disubstituted the monomer and the polymer here in this case, and it has a very planar conformation, and you have a tetrahedral conformation, of course, and this is much more reactive than the monosubstituted vinyl chloride or monosubstituted vinyl fluorides. And if you take a look at the 1,2 disubstituted one, instead of 1,1 disubstituted one, this is 1,2 disubstituted one, right? 1,2 disubstituted one. 1,2 disubstituted one has cis and trans isomer, right? If R prime is placed here with the same plane, this is called cis isomer. Whereas if I have a change in the position of H and R, this is a trans isomer. Although it looks the same, looks very similar because of the double bond, cis and trans isomers are different molecules, different components, different compounds. And cis and trans, if you look at the cis and trans isomer, those have two different reactivities. Trans is much more reactive than the cis isomer. So there are something happen. I said I have elaborated the monosubstituted, vinyl monomer, disubstituted monomer, and I said 1,1 disubstituted or 1,2 disubstituted one, or cis and trans. So the reactivity is different. Now reactivity is different, although I have the same chlorine, in the 1,1 or 1,2 positions. This is due to the static effect. Okay? The reactivity is due to the static effect because the radical could be attacked by the hidden positions. If you have a planar structure, it's much more reactive. If you have a much flexible the conformation or the kinked conformation, then the reactivity goes down. So there are something happen. That's what we can say about the static effect. If you take a look at the cis and trans, delta H, okay, delta H is a little higher for this cis than this trans isomer. Okay? So trans isomer is stabilized than the cis isomer because of the heat of hydrogenation, as you can see here in this case. So planarity is one of the effects. Although delta H is a little higher in cis, the cis is less reactive, whereas the trans is more reactive. So planarity here in this case between the trans is much more affecting the reactivity of the trans isomer. So overall, the reactivity of those substituted polymer is that if you take a look at this value and summarize here in this table, 1,1 disubstituted one is much more reactive than monosubstituted one. In other words, PVDC is much easier to make than PVC. And trans isomer, the trisubstituted one is following the next. And trans isomer is easier to make than the cis isomer in this case because of the reactivity. And this tells us the static effect much more important. Planarity is much more important for our reactivity than others. So this is what I can say about chapter 11 for copolymerizations.